The guard let slip just one word. Yet the person whose chance of living doubled wasn't me, the one who heard it. There's no scary formula in this story. The only tools are addition, multiplication, and calmly splitting things into cases and counting them. In a certain prison there are 3 prisoners awaiting execution. For convenience we'll call them A, B, and C. In an act of mercy, the governor decides to pardon exactly one of the 3 at random. Each has an equal chance of 1/3. Who was chosen is already decided, but the announcement is tomorrow morning, and the only person who knows the outcome is a single guard. Unable to sleep all night, A grabs the guard and pleads, "Just tell me the name of one of B or C who will be executed." The guard hesitates for a moment, then speaks, "B will be executed." At those words A rejoices. "Since only 2 candidates to survive remain, me and C, my chance has risen from 1/3 to 1/2, he figures. But astonishingly, A's chance of surviving hasn't risen one bit. It's still 1/3. The one who actually doubled was C, who wasn't even in the room. Today, by splitting into cases and counting, we'll dig into this absurd conclusion. Peeking at the answer early cuts the fun in half. Just settle on your answer to one question in your head before we move on. All 3 started out at 1/3, and the guard answered that B will be executed. So now what is the probability that A survives? Almost everyone thinks like this. Since B is now certain to die, the survivors come down to just A and C, so it's 50-50, 1/2. Sounds awfully convincing, but the correct answer is different. A is still 1/3 and C is 2/3. Even with B off the stage, A's probability doesn't rise a single millimeter, while C alone grows twice as heavy. It's not a matter of being smart or not. This problem is built so that our intuition stumbles by design. There's a trap hidden in A's reasoning. He quietly treated 2 different things as if they were the same. One is the fact that B is executed. The other is the fact that the guard chose to name B specifically. The 2 are completely different. That B is executed is no news in itself. It was already settled that at least one of B and C had to be executed. The answer he was bound to hear can't change A's own fate. That's why A's 1/3 doesn't budge. Only, no information is true for A's fate alone. The guard's answer does carry real information. It's just that the information points not to A but to C. This asymmetry is the heart of the problem. So why is the only 2 are left, so it's 50-50 reasoning wrong? Because having 2 cases doesn't mean the 2 cases are equally likely. As we'll soon count, a world where C is pardoned produces twice as many chances for the guard to say B as a world where A is pardoned. So once you hear the answer B, the chance that C is standing behind it is twice that of A. Let me spell out one assumption. From here on we assume a fair guard. It seems trivial, but it's anything but. Instead of bickering with words, let's lay out every possible case by hand and count them. It's the most honest way. First, the case where A is pardoned, probability 1/3. Since B and C are both executed, the guard flips a coin and answers B half the time, C half the time. So the case where A is pardoned and the guard answers B is half of 1/3, that is, 1/6. Second, the case where B is pardoned. Since B isn't up for execution, the guard can't name B and always answers C. Third, the case where C is pardoned. By the same logic, the guard always answers B. This case isn't split, it stays whole at 2/6. Now focus on the actual answer B. There are exactly 2 cases that can produce B. A's side at 1/6 and C's side at 2/6. C's side is exactly twice A's side. Split these 2 in a ratio of 1 to 2, and A comes out to 1/3 while C comes out to 2/3. Let's take this in at a glance. A's branch splits in 2 because of the coin flip, so the picture on the left lays out 4 cases in all. The 2 yellow bars on the left are the worlds where the guard could answer B, but their heights differ. A's side is shaved down by the coin flip to 1/6, while C's side stands whole at 2/6. The moment we hear the answer B, we're in one of these 2 bars, and since C's side is twice as tall, the chance that C is pardoned is twice as large. In the picture on the right, before the guard speaks, all 3 sit at 1/3. After the words B will be executed, B drops to 0, A stays right at 1/3, and C surges to 2/3. As the green arrow shows, the share B was holding doesn't split evenly in half. It flows entirely to C alone. Even if we write this out as conditional probability, all we're doing is exactly the same as comparing the heights of the two yellow bars. If A is pardoned, the chance of saying B is 1/2. If C, it's 1. If B, it's 0. We add all of these into the denominator and divide out A's share. The denominator, the total probability that the guard says B, is exactly 1/2. For C, only the numerator changes to 1/3, giving 2/3. We've confirmed it with numbers, but in our gut a question still lingers: why C of all people? Let's draw one more picture. Imagine handing out the right to be pardoned. A gets 1/3, and the remaining 2/3 go into a single basket that B and C share. When the guard said B will be executed and reached in, the basket he reached into was B and C's. He never laid a fingertip on A's basket. So A's 1/3 stays just as it started. Then what about the 2/3 in B and C's basket? It doesn't evaporate, and it doesn't cross over to A's basket next door. The single person left in that same basket, C, inherits all of that 2/3. A was in a different envelope from the start, so A doesn't get a single cent. Let's look at it from another angle too. C was a candidate the guard could have named all along, yet C went unnamed and survived. Could have been named but wasn't. That is the proof of C's good fortune. On the other hand, took A's own name out of the question from the very start. So A's name was never going to come from the guard's mouth in the first place. Don't misunderstand. Being left out of the question by no means makes A safe. A is still stuck at a low 1/3. If it still doesn't sink in, the fastest cure is to crank up the number of people. 100 prisoners and only one pardon. You point at one of them. Then the guard calls out, one after another, the 98 among the rest who aren't the pardoned one, confirms their executions, and leaves just one standing. Now there are two candidates. You, who pointed first with no information at all, sit at 1 out of 100, while the one the guard left standing to the very end is a full 99 out of 100. In the three prisoners problem, C is exactly this person left standing to the end. If this structure feels familiar, you're right. This is mathematically the very same problem as the famous Monty Hall problem, where switching doors is the winning move. Same puzzle exactly, just wearing different clothes. The formulas and analogies may sound convincing, yet you might still suspect it's just clever wordplay. When in doubt, there's one surefire way. Actually run it countless times. By the exact rules. Each game we pick the pardoned prisoner fairly, and the guard fairly names someone to be executed. Then we set aside only the games where he answered B. If A is right, both ratios should hover near 50%. If we're right, they should split into 33% and 67%. We ran 300,000 games, and about 150,000 of them were answered B. Among those, A came out at 33.33%, and C at 66.67%. Let's look at the picture. On the left, as the games pile up, the two curves get drawn toward their own places. The green curve, C, sits near 67%. The red curve, A, near 33%. Neither curve goes anywhere near the gray dashed line at 50%. As on the right, the hand calculation and the computer's hundreds of thousands of runs come out virtually identical. 33 and 67 are facts confirmed from two directions. Now it's time to return to the assumption we laid down in Chapter 2, the fair guard. What if the guard has a habit? Suppose that whenever he's free to choose, he has a habit of blurting out B first. We'll capture the strength of that habit with a number Q. If Q is 0.5, that's the fair guard we've dealt with all along. If Q is 1, he's an extreme creature of habit who always says B whenever he's free to choose. In that case, after hearing B, A's probability becomes Q divided by Q plus 1, and C's probability becomes 1 over Q plus 1. Let's trace in a picture how the two probabilities move as we vary Q from 0 to 1. For the fair guard, right in the middle at Q equals 0.5, A is 1/3 and C is 2/3. But the more the guard likes to say B, the further Q slides to the right, the red curve A rises and the green curve C comes down. And only at the extreme where Q equals 1 do the two curves finally meet at 50%. In other words, the 50-50 A was so sure of was a correct answer only by accident, only when the guard was most biased. A had, in effect, been imagining that extreme. Here comes the deepest lesson. What decides the answer is not the prisoner, but the rule of the one who gives the information. Even on the same words, my probability can be 1/3 or 1/2 depending on the guard's habit. The value of information depends not only on its content, but on how it was selected. So does a habit-ridden guard make a luckier? There's a trap. What if a guard with Q equal to 1 one day says C will be executed? For a guard who always says B to have said C, it can only be the case where B is pardoned and he had no choice. Then it plunges to 0. Hearing the good news B, it's 1/2, but hearing the bad news C, it's 0. Weight these two by their probabilities and add them, and it comes back to exactly 1/3. The conclusion is solid. Whatever habit the guard has, A's overall probability of being pardoned does not budge a single step from the original 1/3. Let's go back to that sleepless night. A felt relieved, but that good fortune slipped past A and flowed to C. It took just 2 tools to topple A's misconception. That B is executed was going to happen anyway, so it was no news, but the fact that B specifically was named was real information pointing to C. And the share B was holding didn't split in half. It flowed whole to C in the same basket. With this we toppled a trap that even PhDs got wrong one after another. A quick word on its history. The 3 prisoners problem became widely known when Martin Gardner introduced it in Scientific American in 1959. Its roots run deeper still. It's mathematically the same as Joseph Bertrand's box paradox from 1889. Here's the fun part. The far more familiar Monty Hall problem is actually the latecomer arriving much later. The 3 prisoners problem is Monty Hall's elder. If math has always scared you, take away just this one thing today. How you came to learn a fact can completely change what that fact means. The moment we ask by what path the same test result, the same single line of news reached us, we see the world a notch more clearly. If you enjoyed today's journey, show your support with a subscribe and a like. See you at the next Odyssey here at ELLS Lab.